Science. And our first presentation will be given by Pavel Sarakovnikov from Irkutsk Institute of System Dynamics and Control Theory of Siberian branch of Russian Academy of Science. You are welcome, Pavel.
Good day, dear participants of the workshop. Can you hear me?
Yes.
Okay.
Yes, now we can see your demonstration.
Okay. Good day, dear participants of the workshop. We are from Atrosov Institute for System Dynamics and Control Theory of Irkutsk. The paper is devoted to the development of hybrid algorithms based on genetic, biogeography, particle swarm, and local search methods for non-convex optimization. The outline of the report is presented on this slide. First, introduction. Then I will give the formulation of the global optimization problems, mathematical programming, and optimal control. Next, I will tell you about the proposed 3 modifications of bio-inspired algorithms. Next is about other implemented nature-inspired algorithms with which the proposed algorithms were compared. Then on the comparative testing of the considered algorithms on the collection of multi-extremal test functions. Next, on the solution of 2 problems of mathematical programming and optimal control from the applied areas of atomic molecular modeling and robotics. Finally, the conclusion. To date, experts have presented a large number of non-convex optimization methods and algorithms of various genesis differing from each other in computational characteristics. One of the subsets of global optimization methods is bio-inspired algorithms. They operate with a multitude of agents at once and represent an alternative to the classic trajectory search algorithms. The basis of any successful search strategy is a balance between global scanning of the feasible set and local refinement of the approximations obtained. The paper presents an approach that applies the advantages of genetic, biogeography, and particle swarm algorithms for the exploration of the admissible set and the limited memory Broyden-Fletcher-Goldfarb-Chanot method for local optimization. The suggested approach makes it possible to create hybrid computational schemes that fully answer the above demands. It is also necessary at each iteration of the algorithm to ensure that the population is sufficiently diverse. For this purpose, biodiversity assessment was introduced into the proposed algorithm schemes. We consider the box constraint problem of global optimization. The objective function f is smooth and non-convex. The presented problem can be helpful in the investigation of optimal control problems in the following statement. The controlled process is described by a system of ordinary differential equations with initial conditions. The problem is to find an admissible control that delivers a minimum to the terminal functional. The first proposed algorithm is the modification of genetic search methods. In proposed modification of this algorithm, the optimization trajectory is built based on the LBFGS method, starting from each point generated according to the genetic algorithm scheme. These slides provide a step-by-step description of the algorithm. Steps that use local descent using the LBFGS methods are highlighted in blue. a measure of biodiversity is calculated at the sixth step. The second algorithm is modification of biogeography methods. Biogeography-based optimization proposed by Simon is a metaheuristic multi-agent algorithm. This algorithm is based on the evolutionary principles of island biogeography, which studies the factors influencing the species richness of isolated communities. The proposed algorithm is based on biogeography and LBFGS methods. Algorithm steps using the LBFGS methods for local search are also highlighted in blue. The third proposed algorithm is a modification of particle swarm optimization methods. To date, quite a few different methods of swarm intelligence have been developed that simulate biological systems. And particle swarm optimization is one of the most well-known and well-proven swarm algorithms. These slides provide a step-by-step description of the proposed modification of particle swarm algorithms. For the numerical study of the properties of the proposed algorithms, some other nature-inspired algorithms were also implemented, which are listed on this slide. One of them is a combined algorithm based on genetic search and particle swarm methods. The developed algorithm is a modification of the genetic algorithm with the addition of a new operator, the idea of which is borrowed from the particle swarm method. In this algorithm, each agent stores the coordinates of the best solution found by him and the best solution passed by all agents. Also, each agent has its own vector of movement speed. Second algorithm is a well-known differential evolution algorithm based on the addition of information recorded in 4 randomly selected agents from the population. Third algorithm is a harmony search that is inspired by the process of musicians seeking harmony in music. Next is uses the specific model of firefly behavior. Teaching learning based optimization is a human society inspired algorithm that operates with multiple agents which are seen as a group of learners. Another population method is a flower pollination algorithm proposed by Young in the source indicated on this slide. And finally, the last of the considered algorithms is a cultural algorithm proposed by Reynolds. All non-convex optimization algorithms are implemented in the C language using uniform software standards. Computational experiments were performed on a computer with the following characteristics. A numerical comparison of algorithms with each other on a collection of test problems is of interest. To do this, we provided the same testing conditions for each algorithm. Firstly, the number of individuals for all algorithms was chosen equal to 10. Secondly, the only stopping criterion for all algorithms is excess of 10,000 calls to the objective function. And, thirdly, due to the stochasticity of the methods, each algorithm on each problem was launched 50 times from the same set of uniformly distributed initial populations. We investigated two variants of genetic, biogeography, and particle swarm algorithms. First variant is an original algorithm with the number of iteration of the local search method is equal to 0. Second variant is combined with the LBFGS methods for local search. The collection of test functions includes, for example, the following problems. The dimension of all problems is 100 variables. The Rastrigin function is one of the most famous separable test models for global optimization algorithms. It is the results of comparing algorithms in the form of box diagrams for this task. Modified and original variants of three algorithms. Diagrams show the mean, the lower and upper quartiles, the variance, the minimum and maximum values of the sample, which represents the results of the algorithms after each run. The vertical axis plots the mean values of the function over the population obtained from 50 lunches. And these diagrams show results of comparative testing of all implemented nature-inspired algorithms, and all variants of the algorithms based on hybridization with the LBFGS methods demonstrated significantly better results than the original ones. Among the algorithms tested, modification of genetic algorithm is leading, giving solutions near to global minimum value. For each problem from the test collection, statistics on lunch were calculated, minimum, maximum, mean values, and standard deviation. Another multi-extremal test problem is the Solomon function. As can be seen from diagrams, the implemented combines algorithms for global search demonstrated significantly better results compared to the original variants. Modification of biogeography-based optimization algorithms is leading among the algorithms under study. This table demonstrates statistics on lunches. Next, the Schwefel function is one of the classic multi-extremal optimization test problems. Genetic algorithm is a leader among the algorithms without the local search, and the developed modification of genetic algorithm increased its performance, showing the best numerical solutions among all algorithms. Its statistics, and for example, stretched V-sine wave function that has a complex system of local optima. As can be observed from diagrams, modifications of genetic and biogeography algorithms are leading and greatly benefiting productivity compared with other proposed algorithms on this problem. Based on the performed numerical study of algorithms, we can formulate that proposed modifications of genetic biogeography and particle swarm algorithms showed significant improvements over the basic variants in all cases. Using the proposed algorithms, we solved the problem of investigating the stable states of atomic molecular clusters. A cluster is a correlated group of elementary particles. In recent years, a large number of mathematical models were proposed focused on various types and microstates and of substances. By now, according to experts, the number of proposed models has reached several hundred. From a mathematical point of view, we can consider these problems as the problem of searching for a global minimum of potential function. The Cambridge Energy Landscape Database source provides computational results for various models with the best of known solutions. One of such problems is to optimize the Saturn chain potential, which is often used in calculating the properties of nanoclusters of various metals. The multi-extremal objective function is as follows. The Cambridge database contains the results of computations for Saturn chain clusters with dimensions from 3 to 80 atoms. We have integrated the proposed algorithms into the three-stage computational technology that was presented at this conference the year before last. A performance check of the implemented algorithms was done with cluster dimensions published in Cambridge Energy Landscape database. The found values coincided with the best of known. And further extra large problems were investigated for clusters with dimensions of more than 80 atoms. This table presents the best values found during computations for dimensions from 81 to 150 atoms. Here is a plot of the best found values versus the number of atoms. The blue line marks the known values published in the Cambridge database. And the red line marks the values of the function at extra large dimensions, which have not been previously investigated by anyone. As can be seen from the plot, these dependence turned out to be close to linear, without sharp deviations from the observed regularity of the found values of the potentials. Also, using the developed algorithms, the optimal control problem in robotics was solved. A mobile robot is an automatic wheeled vehicle that has a moving chassis with automatically controlled drives. This figure shows a model of the wheeled robot. The target point XM is in the middle of the rear axis of the robot platform and has coordinates X1 and X2. The angel X3 formed by the central axis of the platform, and the X1 axis determines the orientation of the robot. The two rear wheels are driving and the two front wheels are responsible for turning the platform. The mathematical model of the mobile robot is described by the following system of differential equations. The phase coordinates must satisfy the following inequalities. The problem is to transfer the system from one point to another in the shortest possible time. We have reduced the optimal control problem to a mathematical programming task. And in the course of the solution, it was possible to obtain the optimal value of the functional and the trajectory, which are slightly better compared to the results of computations given in this paper. Figure shows the optimal trajectories of the mobile robot for the solution found on the plane left and depending on time right. On the left graph in the form of dashed circles, the areas defined by phase coordinates by phase constraints are shown. it's areas beyond which the robot cannot enter. And the arrows indicate the direction of movement of the robot. Thus, three combined algorithms for solving multi-extremal optimization problems were proposed and implemented. Developed algorithms were investigated on a collection of test problems. We used these algorithms to solve problems from the applied fields of atomic molecular modeling and robotics. The obtained numerical results allowed us to demonstrate the efficiency of the proposed algorithms. Well, that's it from me. Thanks very much for your attention. And finally, I will be happy to answer your questions.
Thank you very much for your presentation. Dear colleagues, we have a little bit time to ask questions and get answers.
Okay, may I ask a question?
Yes, sure.
I have a question about potential problem. So you have used different starters to select some initial point. What was the second step? What optimization algorithm you apply after you have one initial point? I mean that if you want to run genetic algorithm, we need a population instead of one starting point. How you create a population in this case?
Thanks very much for the questions. In the implemented three-phase computational technology for optimizing conformation of atomic clusters, we have single point algorithms that we call starters that perform a local descent from the points generated at the first stage. First stage is generating initial points. And also we try to apply multi-agent algorithms. We use multiple of starting points and run one of the nature-inspired algorithms.
Nature-inspired algorithm starts with random points, yes? I'm correct?
Yes, yes.
Okay, but what about start genetic algorithm from some good point? You can get these points by any other starters, and after that you will apply global search, but not from random point, but from some good point. I think it will be more honest, because for local search you use good initial point, but for random search you start from random point and you can be very far from good position. Okay, just for discussion, it's my opinion. Nevertheless, thank you very much. It was very interesting for me.
Okay, thank you. To be honest, I must give possibility to ask another question. Ivan, please.
Okay. Hello. So my question is about the last application you presented. Well, just for me to know. So usually when we're speaking about the trajectory control, we're speaking about synthesizing a regulator. But here you are like solving the direct control problem. So you're trying to find the control function. So my question, so is the time that when you receive the solution is comparable with expected decision-making time? I mean, so robot needs to be controllable online. But when you solve this problem with the global optimization tool, you require some time to have a solution. So is it comparable with what you expect? Is it successful?
Thanks for the question. And this problem we performed optimal time minimizing the discrepancy by the one of the implemented algorithms. And the found solution that is time.
Let me specify. I mean, you need some computational time to find the control. Is this computational time acceptable? Because usually when you control robot, it is online control.
I suspect it's another problem statement. A robot is staying at the place and try to find the shortest path. After finding the shortest path, it starts to go. Yes, Pavel?
Yes, yes.
In this time, in this situation, the time of decision making is not so extremely important.
Not important. Okay, thanks.
Okay, thank you very much, Pavel, for your presentation. Thank you, colleagues, for discussions. Now we have to transfer our attention to the next talk. It will be a talk of as a result of joint project of Japanese and Russian teams from IT Prefecture University in IT Japan and Reshetnev Siberian State University of Science and Technology. And presenter is Dr. Akhmedova. Shahnaz.
Hello everyone, I hope you can hear me now.
Shahnaz.
I'm here, can you hear me?
Okay, if you speak louder, it could be better for us.
I'll try my best, but no promises.
You may share your screen.
So, I hope you can see it.
Okay, we can see. You are welcome.
So, as was already mentioned, I will present our joint research conducted with IT Prefecture University and also with coffee company situated in Seattle, Japan. This work is was done for industrial needs of this company. They wanted to have some research about their customers' evaluation of products made by them. So they kind of asked IT Prefecture University to conduct experiments to gain data, which we later used to formulate some classification problems for them. So yeah, the first of all, for this work, we developed linear party classifiers, which were generated by using a modification of the recently proposed adaptive gain sharing knowledge-based algorithm. This algorithm is was used to solve benchmark problems in CEC 2020 and 2021 competitions, and in both cases it showed good results and was among the winners. So we use this algorithm and the more specific modification to generate neurophytic classifiers, which then were applied to solve the problems formulated by IT Prefecture University and us. And here I will present our experimental setup and numerical results obtained during our experiments. So first of all, I need to describe neurofuzzy systems used in our study. And as is clear from the name, these systems use advantages of neural networks and fuzzy logic theory. As it's well known, artificial neural networks are very popular among researchers for solving classification problems, and they can perform intelligent tasks similar to the human brain. Also, it's well known that they have a high precision and learning ability to process data and find similar features in a given data sets. So, however, there are various reasons why neural networks are not able to solve a given problem. For example, imprecise or vagueness of the input information, or let's say overlapping boundaries among classes. Also, there might be questions regarding the features and their definitions, and so on. On the other hand, the fuzzy logic theory is a generalization of the classical set theory, and it's very flexible in handling uncertainties and incompleteness of information. And although generally neural networks are more efficient than fuzzy logic systems in terms of accuracy, for example, the latter has an advantage in interpretability of obtained results. So in this study, the rule-based neurofuzzy systems use the idea of adaptive neural networks divided into layers that represent the fuzzy inference system. So on this slide, you can see an example of neurofuzzy system and layers that are used during its work. So input layer is obviously membership function layer, classification, declassification, normalization, and as a result, the output layers. The feature space is partitioned into multiple fuzzy subspaces. These subspaces are controlled by fuzzy ifs and rules, and neurofuzzy classifiers generally have multiple inputs and outputs. Therefore, the usage of weight coefficients in the classification layer affects fuzzy rules and improves the classifier's flexibility. So to generate more efficient neurofuzzy systems, the parameters of the fuzzy ifs and rules should be optimized. And in this study, we use the k-mean clustering method to obtain the initial parameters of the fuzzy rules and to formulate the fuzzy rule base. So to get better classification results, the center and the width matrices of the Gaussian membership functions and the weight coefficients of links connecting layers should be adjusted, and it can be done if the process of generation of neurofuzzy system generation is formulated as an unconstrained optimization problem. So the objective function in this case will be the classification error, and obviously it should be minimized. Therefore, in this study, we used the multiplication of the adaptive gain sharing knowledge algorithm to solve the unconstrained optimization problem, which is related to the generation of neurofuzzy systems. Adaptive gaining sharing knowledge-based algorithm is recently developed, and it is a modification of the original GSK algorithm. This GSK algorithm is it imitates the process of gaining and sharing knowledge by humans, divided into two stages, namely the junior and the senior phases. And these phases describe the process of human life, how each person gains information during its lifespan and shares it with others. So let's consider an unconstrained real-valued problem, optimization problem, with aim to minimize some function f of x, where x is a point in the d-dimensional space. To solve this problem, we're using the adaptive gain sharing knowledge algorithm a set of potential solutions is randomly generated in the search space, and this set is denoted as population, and the size of this population it should be predetermined by the end user. It should be mentioned that here each X represents a person, and D is the number of fields of disciplines assigned to this person. So the AGSK algorithm is an iterative method, and therefore at the initialization step, all individuals in the population are considered as juniors, since people have zero level of knowledge at the beginning of their life. Then for each potential solution, or in another words, individual, the number of gained and shared dimensions used both in junior and senior phases is determined, and this number will not change during the optimization process. Later, all individuals iteratively interact with each other and the environment, and they will try to solve the optimization task by changing their positions, which imitates the process of them learning something new. So the interaction between individuals is done through these two phases, junior and senior. Now I try to describe briefly both phases, and obviously we will start with the junior phase. During the junior phase, firstly, all individuals in population are arranged in ascending order according to their objective function values. And after that, 3 different potential solutions from the population are chosen for each individual. To be more specific, for each point which we have in our population, the nearest better and the nearest worst potential solutions are selected. And also one additionally randomly chosen potential solution from the population is selected. The first 2 individuals selected for a given one are responsible for the gaining information, and the last one is responsible for the sharing information about the search space. So on the next step, all chosen potential solutions are used to update the current position of the considered individual, and this is done by using the differential evolution rotation strategy. The senior phase is similar to the junior phase, but in this case, we consider not just nearest 2 potential solutions to a given one, we consider individuals in groups. So this phase is responsible for gaining and sharing knowledge about the search space among groups of individuals. To be more specific, as for the junior phase, firstly, all potential solutions are arranged in ascending order, also according to their objective function values. And after that, sorted population is divided into 3 groups. The first portion of potential solutions is denoted as best people or the best group. The last portion of individuals, which has, we divide it in such a way that the last portion has the same number of individuals as the first portion. So the last individuals are called worst people or worst group, and then the remaining individuals are denoted as the better part. Here on the slide, P is value from 0 to 1, and M is the population size. So for each individual from the population, one potential solution for the best group and another from the worst group are randomly chosen, while the third potential solution is randomly selected from the better part. And after that, all 3 potential solutions are used to update the current one in the same manner as for the junior phase, namely by using similar differential evolution mutation strategy. So basically, to describe the rapid gain sharing knowledge-based algorithm is like applying differential evolution to 2 times to the same population. And This algorithm has two main control parameters used during both the junior and the senior phases. And the patient strategy for both of them is described in the original work. So I thought it's not important to write here all the formulas. Besides, there is also an adaptation strategy for the population size. It is reduced during the optimization process non-linearly. The similar adaptation strategy will be used for our modification to reduce the external set size, which I'll talk about now. So, despite the high efficiency of the AJSK algorithm, there are still ways to improve its search diversity and to enhance its ability to seek the balance between the exploration and exploitation. And for this purpose, the success history-based position adaptation of potential solutions was implemented to the mentioned algorithm. It was proposed to use an external set of potentially good solutions, which is limited in size and updated as the search proceeds. These potentially good solutions have valuable information about the search space, and it's promising region. So it is logical to use this information to update the current population. So first of all, an additional external set, as I said, is created where previously found good solutions can be stored. This external set exists along with the main population, and the maximum number of individuals that can be stored in the external set is predetermined by the end user. Besides, initially the maximum size of the set is equal to the initial population size. However, at the beginning of the optimization process, obviously it is empty. As it was mentioned already, the position of individuals from the population is updated iteratively during the algorithm's work. So if the improved position for any individual from the population is discovered, then its previous position possibly should be possibly stored in the external set. So initially we proposed three different approaches to update the external set. And after conducted experiments, it was established that the replacement of the randomly selected individuals from the external set by the new potentially good solutions is the most successful strategy, which allows achieving better results for optimization problems. And the scheme describing our modification is presented on the slide. Here A is the external set and K is the current size of the set. So solutions from this external set can be used during the junior and the senior phases with some given probability. Additionally, to improve algorithm's efficiency, the size of this set is reduced in a similar way as the population size. And here you can see the formula we used to do that. So now about the problems. The company Coffee Sakura, situated in Seton, was collecting data regarding the process of making the coffee products and the customers' evaluation of these products for 3 months, from July of 2020 till September of 2020, and collected data differed by the type of used coffee beans. Therefore, 7 data sets were obtained. This data were firstly preprocessed by the research group from Aichi Prefectural University. Then they sent us the also collected data, which they could preprocess, and our research group also preprocessed what we got from the Japanese part, and in the end, 31 basic features were distinguished for each data instance. It was established that each data instance can be described by various parameters affecting the taste of coffee products, including external environmental factors, which can influence customers' evaluation. Thus, after preprocessing for each type of coffee beans, 4 datasets were generated. These datasets differed by the number of features from 5 to 31, features describing each data instance. And the aim was to determine which combination of features is the most informative. Besides, customers' evaluations were divided into two major groups, namely negative and positive evaluations. So in the end, we had 28 binary classification problems. All classification problems solved in the study were also solved by alternative approach, such as standard neural network, support vector machines, rule induction method, decision trees, random forest, k-nearest neighbors, and also by fuzzy classifier HEVCO. All mentioned methods, except the HEVCO approach, were implemented in rapid manner. Software and parentheses for them are given on the slide. Besides, additionally, these problems were solved by previously developed neurofuzzy classifiers generated by the Merdeka algorithm. Parentheses for this classification method, I mean Merdeka optimization method, were the same as in the study when it was firstly introduced, due to the fact that the mentioned algorithm uses parenthesis settings showed the best results according to the conducted experiments on set of benchmark functions. And therefore, similarly for neurofuzzy systems generated by the AJSK approach, the population size was also set to 100. And as was mentioned, similarly, the maximum size of the external set at the beginning was also 100. And the minimum size of the set as of the population was set to 12. The probability of using an individual stored in the external set during both junior and senior phases was equal to 5%. So in this study, also the k-means question method is used to obtain the initial parameters of the fuzzy rule base, as I already said it. And so to show how it affects the classification results, the number of clusters was changed from 1 to 7. So from the optimization viewpoint, the number of dimensions of the search space depended on the number of clusters k, and it is shown in this table. Each data set was divided into two sets, training set with 60% of instances and test set with the remaining 40. There were 10 program bounds for each given algorithm, and the portion of classified instances from test sets, namely the accuracy, was calculated. And mean results over 10 program bounds obtained by the neurofuzzy systems generated by the Merdeka approach are shown on the slide. Here you can see similarly mean results over 10 program bounds obtained by the neurofuzzy systems generated by the modification of the AJSK algorithm. And according to the obtained results, the latter showed significantly better results for all problems, regardless of the number of features instances had. This can be explained by the fact that the proposed AJSK modification is more powerful optimization tool compared to the Merdeka approach, and thus it's capable to solve complex high-dimensional optimization problems. Additionally, results of the mean accuracy over 10 program bounds obtained by the other classifiers mentioned on this slide are shown here in these two tables. And numerical results show that the proposed classifier is more successful on the first and the third problems, regardless of the number of features. The same can be said about the second problem, even though the HEVCO approach shows slightly better mean results than neurofuzzy classifiers generated by the AJSK modification, due to the fact that there is no significant difference between these results according to the non-weakness statistical test. On the remaining classification problems, proposed approach achieved better results when the number of features was either 5 or 8, which can be explained by the lesser number of adjusted parameters. And it should be also noted that neurofuzzy systems work better with 5 clusters, regardless of the number of features. It was also established that the proposed approach generally outperforms alternative well-known classifiers in terms of accuracy, as well as the F-score measure for each class defined in most cases. And thus it was concluded that proposed classifiers trained by the modification or the optimization algorithm AJSP are useful for such kind of problems. Here you can see examples, not even examples. Here you can see membership functions for the best found results obtained for the first data sets, and here the membership functions for the best results obtained for the remaining 3 data sets. And yes, so in this study, 7 problems, classification problems were solved, which were provided by, as I said, Sakharov Company and HP Factual University. We solved this problem with different number of features and initial parameters. And in the end, we showed that our approach is is efficient for such kind of problems. Thank you for your attention.
Thank you very much for interesting presentation. Colleagues, we have time for questions, so please. Okay, Ivan Ryzhikov, you may ask.
Thank you. Hello. So I have a general question about the approach. So you solved the classification problem. Can you specify the validation method that you used?
So validation, we first calculate accuracy, which we obtained on each program round. Also F-score for each class, also on each program round. Then we also compared our results not only by mean results, but by statistical one-weekly test. And in the end, we show that generally our approach outperforms other classifiers. The only classifiers that showed any kind of competition to our approach was the Hefka method, which was also based on fuzzy logic theory. And in most cases, our approach was won according to the one-weekly statistical test. So that's how we validated our algorithm.
Let me specify my question again. I mean, when you compare the classifiers, you compare them on test data, right? And when you train them, which one is the better? You look, when you optimize the parameters, you look at the test data, or you have an extra validation data set. So that is the question.
We just divided into 2 sets, trained on the learning set, and then validate results on our test set, which we didn't use during the generation of neural fuzzy systems. But this division between data was done in such a way that all classes were present in both sets. So certification was used and everything was harnessed and how to say it? I don't know.
No, but when you have the train data set and you use optimization, how you optimize? I mean, by which criteria? Error on train or on test or on validation?
We used error on train set, classification error on train set as the objective function for our optimization problem.
But doesn't it mean that your models are biased for this particular test?
No. Why?
Because you compare solutions, how they are better for this particular test.
Yeah, but all test sets are generated randomly, and we do it not all one time, we do it multiple times, and then we only after that we look at our results and what we got. But so if you use cross validation, you also generate some number of sets on which you validate your results. And here it's the same thing, but we just did it separately. So I don't see the big difference here.
Okay, so you use cross validation.
Yeah, of course we did.
Okay, which one?
Basic version, nothing specific.
Sorry, what's basic?
I don't know what's basic for you. We just divided set randomly, as I said.
Okay. So just split.
Just split it. and we did it 10 times. So our results are not just for one kind of one version of split of the state. So we did it 10 different times, randomly again, as I said. So we had, I don't see how our results can be biased in this case.
Random multiply split, not K.
But only for train. Test is left out, right? All right, thank you.
So all data is split into two sets each time.
Okay, thank you for question and for answer. Maybe somebody else would like to ask a question. No, I don't see any raised hand. So thank you very much again, and we will continue. Our next speaker is from MIREA, Russian Technology University, Artem Gorchakov, and his work is titled Biology-Inspired Optimization Algorithms Applied to Intelligent Input Weights Selection of an Extreme Learning Machine in Regression Problems. So please start your presentation. You may start. We don't hear you.
Hello,
Okay,
can you hear
yes.
me?
Now it's okay.
Thank you. Can I share my screen?
Yes. Try.
Thank
Okay,
you.
we can see it.
Can you see the slides?
Yes, everything is okay.
Thank you. My name is Artem Gorchakov. I represent MIRA, Russian Technological University, and our work is entitled Biology-Inspired Optimization Algorithms Applied to Intelligent Input Weight Selection of an Extreme Learning Machine in Regression Problems. The topic of this is the topic of our research. We are going to consider genetic algorithm with tournament selection, particle swarm optimization, and enhanced version of fishbowl search proposed by the authors of this research. The chaotic fishbowl search algorithm with exponential step decay that is proposed by the authors shows more accurate results in solving different optimization problems, especially multi-extremal ones. And the fishbowl search algorithm itself has shown effective results in image reconstruction, neural network structure optimization, and other machine learning problems. The extreme learning machine, which we consider in this research, was originally proposed by Guan-Bin Huan, and is a single layer feed-forward network where weights of connections among input and hidden neurons are initialized randomly. Hidden biases are initialized randomly as well, and the weights of connections among hidden and output neurons are computed using the generalized Moore-Penrose pseudo-inverse operation. This allows to exclude the iterative learning process while selecting most optimal network configuration, and this makes extreme learning machine computationally inexpensive when compared to traditional artificial neural networks. So, random weights initialization in extreme learning machine doesn't guarantee that the obtained neural network architecture is optimal. The goals of the current research include the development of an extreme learning machine-based input weight selection methods based on different biology-inspired optimization algorithms, investigation of the novel chaotic fishbowl search with exponential step decay algorithm performance in comparison with other widely used optimization algorithms, and extreme learning machine generalization capability improvements. In mathematics, optimization is the selection of the best element from some set of available alternatives. For example, when minimizing the function, we search for such x0 that for each x belonging to the search space of a function, the value of f at x0 is less than or equal to the value of f at x. Population-based algorithms are heuristic optimization techniques. In such algorithms, a population consists of agents, and every agent represents a possible solution. The examples of population-based algorithms include genetic algorithms, swarm intelligence algorithms, and ant colony algorithms, fishbowl search, and many others. The known applications of these algorithms include their use in solving continuous optimization problems, including machine learning algorithms, hyperparameter tuning, recurrent neural network training, and other problems. The original version of the physical search algorithm was invented by Bastos Phil and Limonetta in 2008. The aims of the algorithm include the solution of a premature convergence problem inherent to many population-based algorithms and performance improvements. The core idea of physical search is to make agents move towards the positive gradient of the fitness function in order to eat and gain weight. The original physical search algorithm consists of the individual movement operator, the feeding operator, the collective instinctive and collective volitive movement operators that are applied sequentially to every agent of on every iteration, according to the math shown in the slide. So every agent in the population has an associated weight value, and the weight increases if the agent finds better solution of the considered optimization problem. The algorithm hyperparameters include such variables as the individual step size and collective instinctive or volitive movement step size. So the two step sizes that are decaying linearly on every iteration. The chaotic tent map based physical search with exponential step decay is a modification of the original physical search, which incorporates exponential step decay and uses the chaotic tent mapping based pseudo-random number generator. The new algorithm shows superior results when compared to the original algorithm, particle swarm optimization, and genetic algorithm. Chaotic behavior exists in natural systems and in deterministic nonlinear dynamical system. A dynamical system is denoted by a state space, a set of times, and a mapping that describes the evolution of a dynamical system. The Lyapunov exponent metric provides a characterization of chaos in a dynamical system. Chaotic mappings have applications in cryptography, noise generation, and evolutionary computation. We considered 6 different chaotic mappings listed in the table 1 shown in the slide. The bifurcation diagrams of the mappings are shown in the right-hand side of the slide. Bifurcation diagram shows the values visited by a dynamical system as a function of the mu parameter. The values for the mu parameters of the listed iterative equations were selected based on the Lyapunov exponent metric. And the Lyapunov exponent plots for the considered chaotic mappings are shown in the right-hand side of the slide. So if Lyapunov exponent value is positive, then that indicates that the system is then chaotic state. The pseudo-random number distributions produced by the listed iterative equations are shown in the slide. Most distributions are symmetric. However, only tent map produces uniformly distributed random numbers, and that's required by physical search. The considered mappings were benchmarked in comparison with the popular general purpose pseudo-random number generators, including Mersenne Twister, PCG, and Phillips used in the NumPy Python library. The results show the strong advantage of the logistic map, the square map, and the tent map over other pseudo-random number generators in terms of computational speed. In the new optimization algorithm, we incorporate the chaotic tent mapping based pseudo-random number generator in order to generate the initial locations of agents in the search space and to generate random displacement vectors for individual movement of agents and for collective instinctive movement of agents. The study shows that the algorithm produces most accurate results when we use the tent map based pseudo-random number generator. That is also the fastest one. Additionally, in the new physical search algorithm, we use exponential step decay for individual and collective instinctive movement step sizes. The comparison of linear step decay used in the original algorithm with the exponential step decay used in the new algorithm is shown in this slide. The incorporation of exponential step decay allows physical search to achieve better transition from exploration to exploitation while solving an optimization problem. The modified physical search algorithm was benchmarked on multiple test functions for optimization, including the Rastridin, Gribang, Eklis, sphere function, and others. The results are shown in the right-hand side of the slide. They show the superiority of the new algorithm over a genetic algorithm, particle swarm optimization, and the original version of physical search. The new algorithm allows to achieve better transition from exploration to exploitation. So let's move to extreme learning machines. Extreme learning machine is a single hidden layer feed-forward network where weights of connections among input and hidden neurons are initialized randomly, and weights of connections among hidden and output neurons are computed using object and label matrices and the Moore-Penrose generalized pseudo-inverse operation, which we'll discuss later. The weights of connections among input and hidden neurons are represented by a matrix containing random real values of D rows and N columns. The biases are represented by a random D-dimensional real vector. The weights of connections among hidden and output neurons, beta, are computed using the Moore-Penrose pseudo-inverse of the hidden layer output matrix. First, the hidden layer output matrix is computed, denoted by the H later. The metric XL, where every row represents an object from the training dataset, is multiplied with the transpose of the input weights matrix, where every row represents a vector of weights among a hidden neuron and all input neurons. The B matrix is obtained by cloning the bias vector S times, where S denotes objects count in the training dataset. G denotes the activation function. Sigmoid is generally used as the activation function in extreme learning machines. So basically, the bias and the weights are randomly initialized in the traditional implementation of an extreme learning machine, and the beta weights are computed using these matrix operations. We considered 3 regression datasets in order to check if the application of biology-inspired algorithms can be improved in comparison with the traditional implementation, because random initialization of input bytes and hidden biases doesn't guarantee that we get optimal extreme learning machine configuration. Recent studies report that applying biology-inspired algorithms to intelligent bytes and biases selection can improve extreme learning machine accuracy. In biology-inspired algorithms, solving the considered optimization problem, every agent encodes input weights matrix and hidden bias as shown in the slide. The components of an agent vector are allowed to change from -1 to 1. The root mean square error is optimized by the algorithms using objects and answers from the training dataset represented as matrices. So every agent is represented by a large vector containing all the weights and the bias vector of an extreme learning machine. We considered 3 regression datasets: the CPU performance dataset, where every object is encoded by 9 characteristics that can possibly affect the answer; the outer imports dataset, where every object is encoded by 25 characteristics, meaning the object is represented by a 25-dimensional vector; and Boston-Hausen dataset, where every object is encoded by a 13-dimensional vector. We used 10-fold cross-validation while obtaining optimal extreme learning machine hidden neuron count for each of the considered problems. So each dataset was split 10 times into training and testing parts, and testing part size was set to 30% of the original dataset size, and the training part was set to 70% of the original dataset size. The mean absolute error value plots obtained while performing the 10-fold cross-validation are shown in the slide. If we use a too large hidden neuron count, the model, the extreme learning machine model that requires no training, becomes prone to overfitting. And if we use a too small hidden neuron count, the model becomes prone to underfitting. So we applied a genetic algorithm, particle swarm optimization, and chaotic fishbowl search with exponential step decay to root mean square error loss function optimization in order to get optimal extreme learning machine configuration. The hyperparameters of the algorithms were empirically selected, so the algorithms perform equally well in all of the considered optimization problems. The convergence plots of the genetic algorithm, particle swarm optimization, and fishbowl search are shown in the slide for each of the dataset. As we can see, the enhanced fishbowl search, which uses chaotic mappings as pseudo-random number generator and exponential step decay, is able to find the best solutions in the considered problems. The mean absolute error values gathered during 10-fold cross-validation on testing parts of the datasets are listed in tables shown in the slide. During every cross-validation run, the datasets, as I mentioned earlier, was split to training and testing subsets. training size was set to 70% of the original dataset, and testing dataset size is 30% of the original dataset. As we can see, the models trained with enhanced physical search with exponential step decay and chaotic pseudo-random number generator shows most accurate results. In addition, we obtained the box plots of the mean absolute error distributions on test data obtained during 10-fold cross-validation run. As we can see from the box plots, biology-inspired algorithms can either considerably improve prediction accuracy as shown in figures B and C, or slightly improve prediction accuracy as shown in figure A. In order to determine if significant statistical differences exist among the obtained distributions, we applied Wilcoxon-Sangdrang statistical test to the obtained models during 10-fold cross-validation. Significant level was set to 0.05, that indicates 95% confidence level. So the plus sign indicates that significant statistical differences exist among the distribution between the biology-inspired algorithm and the traditional ELM, and the equal sign indicates that there are no such significant statistical differences. So during the presented research, we developed the new algorithm based on physical search, which incorporates the chaotic tent mapping and exponential step decay into the biology-inspired algorithm. The proposed algorithm shows superior results when compared to particle swarm optimization and genetic algorithms and original physical search. We implemented extreme learning machine intelligent input weight selection methods based on the new physical search algorithm, particle swarm optimization, and genetic algorithm. In these methods, input weights and hidden biases of an extreme learning machine are presented as an n-dimensional real vector, where n denotes the number of connections and biases of an extreme learning machine. So we investigated the performance of biology-inspired and traditional extreme learning machine configurations in regression problems. Extreme learning machines where input weights and hidden biases were adjusted using the physical search algorithm with chaotic pseudo-random number generator and exponential step decay showed most accurate predictions on test data. So the new extreme learning machine characterizes by enhanced generalization capability. Further research could cover additional performance investigation of the considered biology-inspired algorithms, as well as automation of hyperparameter tuning of biology-inspired algorithms in order to produce self-configuring meta-heuristics. Finally, the tent map-based pseudo-random number generator could be used in order to improve the performance of other biology-inspired optimization algorithms, as such pseudo-random number generator is fast and produces more uniformly distributed random numbers. And that might positively affect the optimization results. Recent studies report that chaotic random number generators can also be used to generate more uniformly distributed input weights and hidden biases, and this might slightly enhance extreme learning machine performance without introducing additional computational costs. And worth noting also that extreme learning machines where input weights and biases are selected by biology-inspired population-based algorithms are more computationally expensive compared to the traditional implementation, but they can produce more efficient models, more accurate predictions, and extreme learning machines with better generalization capability. So thanks for watching the presentation. Ready to answer the questions, if any.
Okay, thank you very much for an interesting talk. If anybody would like to ask a question, you may start right now. We have enough time. Okay, I will start. Maybe somebody will continue my question. Okay, as I know, when we train extreme learning machines, we train only output layer, and input layer stays random. So don't you think that when you introduce adjusting of input layer, you come to standard backpropagation, standard feed-forward network where you can tune any layer of weights. Maybe I have missed. Can we compare such approach with a standard neural network where we tune the whole range of weights?
Yeah, thank you for the question. Yeah, the comparison really both comparing the extreme learning machine and the biology optimized extreme learning machine with traditional artificial neural networks. And we are planning to do this later as a part of our next studies. So yeah, that's an interesting question. But the idea of extreme learning machine is to use their matrix operations to achieve better generalization capabilities. So probably, of course, we haven't yet gathered the results comparing artificial neural networks, traditional that are trained using granite methods. But in studies performed by other authors, they show that extreme learning machine have better generalization capability compared to artificial neural networks. They are less prone to overfitting due to the way the output weights are computed. So also the influence of hidden neuron count is a subject of current studies, because if we select a too large neuron count on the hidden layer, our model becomes prone to overfitting. And if we find a balance, then our model shows great generalization capabilities without introducing the potential for to be overfitted. So in general, we expect that extreme learning machine is a more overfitting prone neural network architecture, as the original authors of extreme learning machine report in their paper. So I hope I managed to answer your question. But yeah, that's the subject of further studies, and we are planning to gather more results.
Okay, I see. Okay, somebody else want to ask a question? Okay, Ivan.
Yes, I have a question.
Please.
Yes, about fighting the overfitting. Are you assuming to compare your approach with the most common now, like regularization or dropout? Or because it's interesting, you say that we wanted to fight overfitting. Usually we kind of use a combination with cross-validation and I don't know, simplification of the neural net. So it's just very difficult to say that we are fighting overfitting without looking on what we have on the cross-validation. So okay, coming back to my basic question. So would you like to compare those approaches?
Yeah, it's a great idea. So it's really worth studying more. And of course, if we use extreme learning machine, we of course should use cross-validation. In this research, we used tenfold cross-validation, and during the comparison with traditional artificial neural networks that are trained using either population-based algorithms or gradient methods, also both comparing the splitting the data sets to training and testing parts. But in general, the traditional neural networks have loss surfaces that are that have a plenty of local minima, and the convergence towards the local minima to an incorrect local minima can lead to suboptimal results or suboptimal network configurations. And extreme learning machine doesn't suffer from that problem, as due to the nature of which their weights are computed. Also, one of other approaches is to use Tikhonov regularization for ill-posed problems that can further improve extreme learning machine prediction accuracy on the data that it has never seen before. So it is also the subject of further studies. So we considered the extreme learning machine with the traditional training scheme, where we use the generalized pseudo-inverse, which includes transpose of the matrix, then the inversion of the matrix, and then multiplication with the same transpose matrix. And modern researchers are also looking at the Tikhonov regularization applied to the matrix during performing the pseudo-inverse. So yeah, comparing various approaches, the regularization of extreme learning machines and with regularized artificial neural networks is also a subject for further research. And thank you for mentioning that.
Okay, thank you.
Okay, more questions? We still have a few minutes, so I would like to ask another question. This one is about optimization. What was the reason to choose particle swarm optimization algorithm? I mean that if we look through some competition on global optimization, we can see that top ranking algorithms use differential evolution. So again, in next research, maybe you will compare, because we can see that many competition winner algorithms use differential evolution. Maybe you know some advantages of fish school algorithm.
The original authors of the fish school search provided a comparative study of fish school search and the original version of fish school search and differential evolution in image reconstruction of electrical impedance tomography. So we looked at these results and showed and took the algorithms into our comparison in our study that showed the best results there. But yeah, differential evolution is an effective algorithm that has shown its superiority over other algorithms in different machine learning problems. So yeah, probably worth introducing additional comparisons, so including other effective optimization algorithms. They probably can produce better solutions. So thanks for noting that.
So we need to move to next presenter. So thank you again for a very interesting presentation.
Thank you.
Our next presenter is Elena Tulbis from Reshetnev-Siberian State University of Science and Technology, and the work is titled Online Clustering Algorithm with a Greedy Agglomerative Heuristic Procedure and Special Distance Measures. So you can share your screen and you can start.
Good evening, colleagues. This is my presentation.
Okay, we're still waiting. We see black screen.
A few seconds, maybe. Start again.
Yes, now it's okay.
Okay. There are industries with increased requirements for product quality, where solving clustering problems requires obtaining the most accurate and stability result and stable result, such for instance, rocket engineering industry. And the search for clustering algorithms with high accuracy and stability of results is one of the problems of automatic grouping of products. In our work, we consider the use of greedy heuristic procedure with special distance measures for tasks of product clustering based on Kohanen network. Clustering problem formulates as based on similarity or dissimilarity measures, divide M objects of a certain set into K disjoint subsets so that objects of one subset have characteristics similar to each other and do not have them with objects from other subsets. And most of the popular clustering models are the location theory models. The clustering result depends on the initially selected number of subsets as well as the selected measure of similarity or dissimilarity. To date, algorithms have been developed for continuous location problems. In most cases, use common distance measures such as Euclidean distance measure or Manhattan distance measure. However, taking into account the characteristics of the feature space of a specific practical problem when choosing a distance measure can lead to increase in the clustering accuracy. One of the most famous clustering models is the K-means model, which was proposed by Steinhaus. And the goal of this problem is to find K points, we call centers or centroids, in a D-dimensional space or N-dimensional space, such that the sum of the square distances from known points or data vectors to the nearest of the required points to reach a minimum. This optimization model can be considered as a location problem, where it's required to place the points X sub J into an optimal way. The problem is well studied. The K-means problem was algorithmically implemented by Lloyd. In location theory, Weisfeld proposed an iterative procedure for solving similar Weber problem based on iterative weighted least squares method. Local search methods can be used for solving location problems, and the standard local descent algorithm starts with some initial solution, and at each step of the local descent there is a transition from current solution to a neighboring solution with a smaller value of the objective function until local optimum is reached. Local search methods were further developed in so-called meta-heuristics, in particular search algorithm with alternating neighborhoods, or so-called variable neighborhood search. It's my idea to change the neighborhood function in some way that leads to the corresponding changes in landscape during the local search. Gritty agglomerative heuristic procedures are methods to improve the result in a certain neighborhood of the solution. For subsequent iterations, its method choose method that gave the best increase in objective function and at the previous iterations. Agglomerative procedure starts with some solution containing excessive number of centroids, which means excessive clusters. And defining this number of excessive centroids is one of the main issues of this approach. The agglomerative approach used to sequentially remove excess centroids, and the elements of the clusters related to removed centroids are redistributed among the remaining clusters. The gritty strategies are used to decide which clusters are most similar to be merged together. In clustering problems, the key concept is the concept of matrix of objects. Metric is a function that determines the measure of the distance between objects in the metric space. Metric space can be defined as a set of points with a distance function d. Many distance measures based on Minkowski distance measure. In our experiment, we use different types of this distance measures, like Euclidean distance is a Minkowski distance with a parameter p equal to 2, squared Euclidean distance. Manhattan distance is a Minkowski distance with a p equal to 1. Chebyshev distance with p equal to infinity. And Mahalanobis distance, which is a special case. This distance is equal to 0 for a point at the mean of distribution and grows as a point moves away from the mean along each principal component axis. Mahalanobis distance is unitless, scale invariant, and takes into account the correlations of the data set. Mahalanobis distance calculated as a dissimilarity measure between vectors x and y of the same distribution with covariance matrix C. If the covariance matrix is diagonal, then the Mahalanobis distance turns to Euclidean. In our study, we consider applied problem of automatic grouping of products, electric radio components, coming to specialized technical test center that carry out different diagnostic operations. And the identification of the original homogeneous batches of products made from the same raw material is one of the most important steps during testing in this center. In our earlier studies, we used affine clustering methods to divide the homogeneous batches of products. In this work, we propose the following idea for organizing the work of the test center. Purchased lots of products arrive at the test center one by one in inline mode. We discover an inline approach to group products to homogeneous batches. Online clustering is a fundamental problem in many online or streaming data analysis applications. Characteristics of online clustering are real-time processing and reception of data during the operation of algorithm. So compared to traditional offline clustering, online clustering algorithms should frequently update clustering results. For our algorithm, we used as a base Kochen network. Kochen network referred to self-organized neural networks, which allow to allocate groups of input vectors with some common features. And the Kochen network is a single layer network, each neuron of which is connected to all components of the n-dimensional input vector, or it's a class of neural networks, the main element of which is the Kochen layer. Kochen layer consists of adaptive linear adders or linear formal neurons. And the Kochen networks use unsupervised learning and the competition mechanisms for training with a principle winner takes all. According to the methods of adjusting the input weights of the adders and the problems being solved, many varieties of Kochen networks distinguished. The most famous of them are vector quantization networks that are closely related to K-means method. Self-organizing Kochen maps that provide the topological mapping from the input space to the clusters. Neurons in sums organized into a grid that are usually two-dimensional. And learning vector quantization networks, which include supervised learning and used for classification problems. Kochen network of vector quantization type is often used for inline clustering. In this case, a set of initial data is not stored in memory, but processed immediately. Here, the input vector X is a description of one of the objects to be clustered. The number of neurons coincides with the number of clusters that the network should allocate. Linear weighted adders are used as neurons, as I said. Each neuron is described by a vector of its weights, W, where M is an input vector dimension. And when the vector X is fed to the network input, the neuron wins the weight vector of which is the least different from the input vector. This problem with P key vectors, code book vectors, W, in the feature space of the observed data X is defined as following minimization problem 1, where P sub j consists of points X closest to W. The main algorithm of online Kochen network training consists of 3 steps. Firstly, we have to find the closest neuron W to data point X. Each item of X is processed one at a time, and for each of them, the nearest vector W determined. Then Secondly, we update the closest neuron using following formula 2, where nu is the learning rate, and the rest of key vectors do not change. An online method with a damped learning rate used to ensure stability, where learning rate is a function of the number of learning steps. And thirdly, we have to return to step 1 if there is unconsidered initial data. In this work, we propose to use the greedy agglomerative heuristic procedure in the online method. So we have to set the number of neurons, increase the number of neurons in cut times, then set the weight of each neuron. In this algorithm, we make this randomly. Determine the number of steps to calculate the learning rate. And then we start to allocate data vectors one by one, update the closest neuron, and recalculating sum of distances to the data set. After a certain step, the neuron is removed, the removal of which shows the smallest increase in the value of the objective function. This algorithm was implemented in Python. And for the experiment, we considered the sample consisting of 4 different homogeneous batches of electronic radio components. The total number of devices was 446. Total number of device input parameters was 62. We considered various combinations of batches, mixed lots from 2, 3, and 4 batches. Each experiment was performed in real time online method with an initial number of neurons P, marked as online clustering on the picture. Online method with an initial number of neurons exceeding the specified number of clusters by 2 and 3 times were used. Each experiment was carried out with different types of distance measures. For various combinations of batches, each experiment was run 30 times and the results were averaged. Computational experiments showed that clustering accuracy decreases with increasing number of homogeneous batches in a mixed lot. In a 2-batch separation task, all distance measures except Chebyshev showed unmistakable results. In a 3-batch separation task, on the contrary, Chebyshev distance showed much better results than others. In 4-batch separation tasks, the Manhattan distance gave worst accuracy among others. The use of greedy agglomerative heuristic in online clustering, in most cases except square Euclidean, improves slightly the accuracy of batch separation. Also, for various combinations of batches, the coefficients of variation and the span factor of the objective function calculated. For 2 batches, the coefficient of variation and span factor is minimum for Chebyshev and Maslov-Nobis distances. For 3 batches, the coefficient of variation and span factor is minimum for Manhattan and squared Euclidean distance. And in the case of 4 batches, the worst maximum value demonstrate Chebyshev distance, and other distances are similar to each other with slight advantage of Maslov-Nobis distance. We can say that in our work we propose a line algorithm for clustering products based on Kohanen network using greedy agglomerative heuristic procedure. And the studies have shown that used distance measure in most cases doesn't significantly affect the clustering accuracy. And the computational experiments showed that the use of the greedy agglomerative heuristic in online clustering in most cases slightly improves the accuracy of homogeneous batch separation. The study of the online algorithm for clustering products on a large number of homogeneous batches is an interesting area for research. Thank you for your attention.
Thank you for your speech and presentation. So we have time for questions. Please, you may ask. Yes, Ivan, please.
If nobody have a question, I have a question about how you compare the results. Do you use random initialization for the coordinate maps?
Yes, we used random initialization, so we have to run this algorithm for 30 times and averaged results.
Okay, so those figures that we've seen, those are averaged.
I'm sorry?
I mean, the results of comparison between different metrics and so on, those results are averaged.
Yes, it's averaged results.
Okay, then a suggestion, probably if it is average, that would be also interesting to see the distribution, like the quartiles and the median values.
Yes, thank you for the question. This indeed is interesting, maybe, and we just forgot about this. Maybe next time.
Okay. Okay, thank you.
And let me add as a co-author. Actually, there were several types of initialization, including deterministic ones. There were deterministic initialization and also random. If for random initialization we ran 30 times of each algorithm.
Okay. And for deterministic initialization, are there any difference with the random? Other results are different.
The results was similar.
Similar. Okay. Okay. Thanks.
Okay, I have one more question. You solve optimization problem, and as I understood, when you get new data, you have some changes in your objective functions. That's why you need to adapt to these changes. So it seems to me that when you have a small portion of data, you have just small shift. That's why some greedy and local search algorithm will help you to find a new optimal solution. But what about if you get a big portion of new data? And in this case, you can have very different objective function. So you need to start your optimization problem from some initial state, for example, from random point and so on. What type of problems you discuss? It's a small changes or some huge changes in objective function?
Yes, we are studying this problem now because it's just first steps in this direction. So the sample we used in this research is not so big, just 446 products. And for further research, we use bigger samples. So for these purposes, we are constructing several types of initialization, not only random, but pre-initialization with some algorithm that can give some start solution from which we can further develop our division in our sample.
I will also add something. Here, the data come one by one. The portions of data are similar. Just one more data point, one more data vector. The idea was just to try the greedy heuristic algorithms for online data processing, because for offline data processing, they sometimes give 3 times as better results than classical k-means, for example. The Kohanen networks are very useful for online processing, and this was just the first try to adapt the greedy heuristics for such kind of data. Of course, if it is really efficient, we will try to adapt them for large amounts of data. It was just to try if it works or not. It does.
Okay, maybe I was confused by word batch. I mean, it's some hundred of thousands of electronic devices.
Batch, this is the problem of our electronic industry. Okay. For space. The batches are usually small.
Okay.
And we must use small data. Big data are easier to process.
Okay, I see. Okay, somebody else? Do we have any questions? Okay, just look on the list. Okay, we have a few minutes. May I ask one more question, very short. There is no significant differences in choosing metrics. Is this a result of a new greedy approach, or it's some specific real-world problem?
So maybe... I think it's specific of data.
Okay.
We used.
Okay, I see, because it's look like we have to get to see this difference, but if it's no, maybe it's
actually we try to process this data during several years, and there is no answer which metric is the best to use, which clustering model is the best. So we usually use an ensemble.
Okay, but we can see from results these bar plots almost the same. That's why you can conclude that difference is very small.
This is a special case probably for different data sets. The difference is different.
Okay. So thank you again for your presentation, for answers. So I think we can have 2 minutes break. Just maybe you would like to move or drink something, and we will continue. Our next presenter will be Tatiana Karaseva. So I will announce it a little bit later. Let's have 2 minutes break. Well, I think we can continue. Tatiana, please share your screen. Okay, let me announce next speaker, Tatiana Karaseva from Siberian Federal University, and the paper is titled Application of Evolutionary Algorithms for the Identification of Differential Equation Systems.
Good evening. Can you see my screen?
Yes, everything is okay.
Good evening, dear participants. The theme of my report is Application of Evolutionary Algorithms for the Identification of the Differential Equation Systems. You can see the plan of my presentation. A dynamic system is an object or process characterized by its state as a set of characteristics at time-certain points. The law of the dynamical system state evolution in time is determined for them. Examples of dynamical system can be found both in the natural sciences and in computer science, economics, and social sciences as well. The law for the dynamic system state change in time can be given by a differential equation. But often in a real process, the output of a dynamic system is characterized by several variables. It is necessary to apply a representation in the form of a system of differential equation to build a model of such process. The value of the model in the form of a differential equation and their system is in the symbolic form. So it is possible to study the nature of process and evaluate a degree of conformity to the known laws. Various approaches have been developed and applied to search for a model of dynamic system. The most significant groups of such approaches are parametric and non-parametric methods. Parametric methods require a priori information about the structure of the model. The search for a model is in the selection of parameters of an already predetermined structure. A large number of requirements are imposed on the data using non-parametric methods. But the quality of modeling depends significantly on such samples' properties as its volume and the presence of noise. This work proposes a new approach based on genetic programming algorithm for identifying dynamical system in the form of a system of the first order differential equations. Consider the problem statement. Let there be a sample of values of volume n describing the behavior of a dynamic object, where x's are inputs of the dynamic system and y's are the outputs of the dynamic system at moments of time t sub I. The object can be described by a system of differential equations. The order of the differential equation is considered bounded. It is necessary to build a model in the form of a system of differential equations that correctly reflects the relationship between the inputs and outputs of the system. The initial conditions are assumed to be known. Let us present a description of the proposed approach for identifying a system of differential equations. This approach will be based on a self-configuring genetic programming algorithm for identifying a differential equation. The essence of this approach is in the formation of an individual, a tree that encodes a differential equation. The tree is built with sample data describing the behavior of the object. And I should note that this approach let operate with differential equations of arbitrary order. The functional and terminal sets are redefined to using the genetic programming algorithm. The terminal set includes a set of all input and output variables, a set of constants, and derivatives. The functional set consists of the functions used by the algorithm to form the solution. The root vertex of the tree contains not only an element of the functional set, but also the information about the maximum order of the derivative for the given individual. An example of a tree is shown in a figure on this slide. The evolutionary steps of the algorithm were also substantially modified for the genetic programming algorithm operating with differential equations. A starting population is generated randomly from the given number of individuals at the initialization step. A node of the differential equation is not higher than the given value of k in the root node. An individual in the form of a tree is converted into a formula. Then the fitness value is calculated for it. The calculating derivative must be performed at the points of the initial sample in calculating an error of correspondence of the found solution to the true one. In this approach, the output estimation of the differential equation from the points of the initial sample x(i) was performed using the fourth-order Runge-Kutta method. The peculiarity of the mutation in the approach is a possible change in the root node containing the maximum order of the differential equation. In case of a change, mutation of the maximum order of the differential equation, the order of the derivative must also be changed. So, in figure on this slide, a mutation of the maximum order for the given individual will entail a change randomly choosing of the order of the derivative lower than a new maximum order and other selected vertices. Thus, the genetic programming algorithm for identification of differential equations can be the basis for the concept of dynamic object identification development in the form of differential equations system. An example of the differential equation system encoded in the form of trees is presented in figure on this slide. Consider a scheme describing an approach for the identification of differential equation system. The proposed approach provides a combination of several genetic programming algorithms described early. K genetic programming algorithms are required for K equations in the system. Each algorithm searches for one of the equations of the system. The number of equation n corresponds to the number of output variables in the data. Then a population of individuals is formed in each genetic programming algorithm, and their potential representations of each of the n differential equations in the system. The fitness for all individuals of each population is calculated. One-time complete enumeration of all possible combinations of individuals. The order is not taken into account. The best individual is determined. The best individual is determined on the basis of the obtained values in each population. Further evolutionary steps are implemented: selection, crossover, and mutation. After the implementation of the evolutionary steps, the fitness is recalculated. The calculation of the fitness for each individual of each population is carried out by substitution in each of the equations of the system. The best individuals are selected as the remaining equations in fitness calculating. Then the specified stop criterion is checked. If it is not met, a new cycle is implemented. When steps 2 and 3 are implemented, the numerical coefficients of the equations of the system are optimized by the method of differential evolution. A vector to be optimized contains the numerical coefficients of all equations and the initial conditions contained in the system, a current combination of individuals. And I should note operation with only the first order equations is possible at this stage of the algorithm development. The proposed approach implies a self-configuring type of evolutionary algorithm. The success history adaptation algorithm is applied for genetic programming and differential evolution parameters containing numerical values. The population level dynamic probabilities method is applied for parameters with a choice of type. The first order differential equation system were used to identify samples of values were generated for these systems. Samples of values were generated for the systems of equations to study the efficiency of the proposed approach. Two types of samples were generated for each task: without noise and with 5% normally distributed noise. For each task, 10 runs were performed. The number of individuals was 50 and number of generations was 100. As a stop criterion, we select an error which is less than 500. The following criteria were selected to investigate the efficiency of the approaches. There are an error and average generation number where the solution was found. Table and diagram on the slide contain an error and generation number average over 10 runs. Consider output of the models obtained in runs. Figures on slide shows that correspondence of the obtained models with the highest and the lowest errors to the true values. This work proposes a new approach to the identification of dynamic object in the form of the differential equation system on the basis of evolutionary algorithms. A system of differential equations help to describe the behavior of the system with several output variables. The proposed approach does not impose restrictions on the form of equations included in the system, which allows it to be used in the identification of dynamical system with an unknown structure. The genetic programming algorithm makes it possible to obtain a model in symbolic form for its further research. The next stage of our research on the proposed approach is a modification of the genetic programming algorithm to work with systems of differential equations of arbitrary order. Thank you for your attention.
Okay, thank you very much. We have a question from Lev Kazakovtsov. Yes, please.
Yes, could you please open the page number 8? No, probably 7. Yes, this one. As I understand, the coefficients in your differential equations, they take part and they are processed in the usual genetic operators like selection, like crossover and mutation. And moreover, for the coefficients, you use also special optimization with the differential equation. The first question is, how do you use the differential equation? Do you use it for each thread separately, or there is a big population for all the threads in your algorithm? I mean, GP1, GP2, and so on. Is this an evolutionary algorithm inside another evolutionary algorithm? Or I don't understand something.
Yes. We use differential evolution for each trees, for each population, for each genetic programming.
At each iteration, yes?
Yes.
Isn't it too complicated? I mean, computationally complicated. Isn't it better to use, for example, local optimization of the coefficients?
No, we investigate this question, and differential evolution provide better results.
Of course, it provides much better results, but it is probably too computationally difficult. It is a heavy optimization method. Probably it's better to use, for example, random shift mutation or local search. It looks strange, but thank you. Thank you very much.
May I add something?
Yes, please.
As our rector said that once, 35 years ago, it was very important to use an approach that bring us not to the case to spend very expensive computing time. But it's of course not a question for now. The main idea is here that if we lost precision thanks to local improvement of coefficient, during the first stages, we will never come back to the really good answer later. That is why there is a necessity to try to find at least good approximation of global optimum for coefficient at each stage, instead of, let me say, precise local optimum. Because of we can leave the attraction zone of real answer in this case because of not precise estimation of numerical coefficients.
Yes, probably, but there is two ways of to avoid the attraction of local minimums in this algorithm. The first is the big iterations, these GP1, GP2, and so on. And sometimes it's better to use more big iterations rather than try to search for the most precise result in the small iterations embedded into other iterations. It's always a question.
The key word here is sometimes. It is not the time for this approach, for our approach.
Okay, thank you very much.
Another case.
Okay, we have one more question from Ivan. So please.
Hello. Sorry, can't have camera anymore. Well, I have a question about the problem definition, because it seems like it's not identification problem, but a regression when you compare the Cauchy problem solution to the observation data. I will try to specify. You are working not with linear dynamical system, but with non-linear. And in that case, you cannot guarantee that the system you have in the result, which is close to observation, is even close to the real one. I mean, it would be perfect that in your research, you compare how does the system react on different control and compare it with the original system. Because when we're talking about linear system, we know that it should be exactly the same, but with non-linear system, it can be completely different. So you can have a system which is really close to observation data, but it is far away from the real one because it's non-linear operator. It can have different reaction on different control, really different from the original system. You can even try just have different initial values for the differential equation and see if there is any difference. So this is like my opinion of what happened. So the question is, have you tried this comparison? Like you identified a nonlinear system and now you can give it different control and compare how it reacts and compare this output with output of original signal, with original system that produced the signal that's used for observations. Have you tried to compare these two things?
At this stage, we built a model that then derivative to original differential equation good, but this is not symbolic accuracy, but approach to identification differential equation provide symbolic accuracy. And I think we can we can develop the algorithm for this approach. Then provide a symbolic accuracy to real object.
Okay. I will try to specify it one more time. So the question with a nonlinear system is not how good you have a fitness function, or even if the symbolic equation is the same or not. It's not the point. The point is how you actually estimate the nonlinear operator, which you can justify only by having different controls. Because with linear system, you know that if you can identify the transient process, it doesn't matter if the linear system is exactly the same or it have different order or something like that. So you don't care much about it because you know the transient process. For nonlinear system, there is no such thing as the transient process that ends. I mean, so that's why I think that you could try it later just to see how far you or close you are with your solution. Just try different controls input, different initial values.
Okay, I think it's a advice for further investigation.
Yes, exactly. It is not the case for this stage of a reported research. Certainly you are right, but without this stage, we cannot come to questions to solve, likely you said.
Okay.
Well,
thank you.
Thank you for question and for answer. May I ask a question? Two questions. First is a technical one. On this picture, on this slide, we have error. It's mean error. Do we need square here? When you calculate fitness function, I mean formula for fitness function. Okay, do we need to have this difference squared? I mean, you can have a positive and negative value here in this sum.
Yes, you are right.
Okay, it's mistype. Okay, and
yes.
And fitness 1 minus error. If you have error equal to 1, that means you will divide by 0. It's I think it's not correct sign here. Yes.
Excuse me, why not?
If error value is equal to 0, you will divide fitness 1 divided by 0. So I think you need to have 1 divided 1 plus error. In a case you have positive error, you will have 1 or some another value. Okay, it's technical. I see it's. I think it's mistype, just mistype. It's not something specific about fitness. Okay, my main question. You solve system of equations.
No, no solve.
No, okay.
Identify.
No, so identify. I mean that when we say system, it's a set of some agreed equations. But as I see on this picture, we solve many independent problems. Do we somehow try to understand if these separate equations are agreed as a system, or just a set of many different independent solutions? Okay, how you understand that you get a system, not just a set of equations, but you have a system of equations?
So we have a system of equation, and of genetic programming search one equation of system, and fitness calculation provide systematization of this equation.
as you can see in error, there is a sum from I equal to 1 to K. It's the summarized error of all K equations. You see, GP1,
yes,
GP2.
I understand, but I think you may get many different superposition of this function. For
yes,
example,
and they occasionally view really good for all equations at the same time, yeah?
Why not? It means you have a lot of local optima with very close error.
That is why we use a differential evolution instead of having many local optima.
Or many global optima. Okay, I see.
Yes.
Now I see. Okay.
No, in any case, certainly we need investigation further because from the, how to say, within the problem of identification, now mainly the problem of generation of equations has been resolved. Yeah, and of course, Ivan is right, and you are right that next stages we should specify the problem to have exactly system of equations and to understand how does it react to different inputs for the system. If you have additional data for the same system, of course, we will check. Now is the starting point. Without this point, is it impossible to go further?
Maybe as advice for concerning my question, you can try some cooperative coevolution, which will involve such cooperation of different equations to get the whole system as a system, as a kind of agreed solutions. Okay, just an advice. Okay.
Yes, of course. Thank you.
Thank you. I think Professor Semyonkin will announce our last presenter. Professor Semyonkin, would you like?
Yes, of course. I'm here. Our next presenter is Lev Kazakovtsev, who will present the result of joint investigation of the IWMMA University in St. Petersburg and Reshetnev Siberian State University as well as Siberian Federal University. 3 universities representative within one research. You are welcome.
I cannot enlarge my screen somehow. I don't know why. Can you see the screen?
Oh. Yes, we can see.
Aha. Very good. So I present our joint investigation about 1 plus lambda evolutionary algorithm. To say the truth, this is not a true 1 plus lambda evolutionary algorithm, but it uses the same scheme as the 1 plus lambda evolutionary algorithm with the greedy agglomerative mutation for the p-median problem. We consider only continuous p-median problem in this work. This is a popular mathematical model for both facility location and cluster analysis. As a model of cluster analysis, as a model of unsupervised machine learning, it is less sensitive to the outliers than the k-means model. For the p-median problems, as well as similar problems like k-means or k-medoids or problem of searching for mixed distribution separation, there are several popular algorithmic schemes like variable neighborhood search, algorithms like J-means and others. And the greedy agglomerative heuristic procedures embedded into genetic algorithms. They demonstrate very precise results in comparison with the other algorithms for many practical problems. First, what is the p-median problem? Very simple problem. We have several data points, AI on this slide, in a d-dimensional continuous space. And we have to find p points in the same space so that the total distance from the given points, we call them demand points or data vectors, the total distance from these points to the sought points, to the closest of the sought points, reaches its minimum. This is the scheme of this problem. On the right, here we have several blue points, and we have to find.
I'm sorry, something's wrong with your presentation. Maybe you should put F5.
One moment, I'll try to start again. I mean, a demonstration of the screen.
Yeah, because it's slides, but not demonstration.
I see.
I think you need to share the whole screen.
Yes.
Yes. Okay.
Yes. Is it visible now?
Yes.
Okay. So this is the scheme of the problem. We have several blue points, and we must find, in this case, 3 red points to minimize the total distance. On the right part, we have the interpretation of this problem as a clustering problem. There's a subset of blue points with the same closest red point are the cluster. There are several settings of similar problems. We consider only a continuous problem. There also exists a network p-median problem and the discrete version of the continuous problem, p-medioids problem. In this case, we search for red points, for centers of the clusters only in a finite set. Very close problem is the k-means problem. In this case, we have total squared distance instead of total distance. I mean, sum of distances. And the k-means problem is computationally easier. It is less complicated computationally. The most popular algorithm for all those problems is the alternate location allocation algorithm, or Lloyd algorithm. It is an algorithm of 1950s, but published only in 1980s. Two-step algorithm, very simple, with 2 alternating steps. In the case of the continuous p-median problem, to find a center of each cluster on each iteration of the ALA algorithm, we have to solve the Weber problem. And the most popular and the simplest algorithm for the Weber problem is the Weisfeld procedure, iterative Weisfeld procedure. So we have an iterative procedure embedded into other iterative procedure in the case of continuous problem. This algorithm is highly dependent on the initial on the initial solution. To improve the results of this algorithm, we can use multi-start of the alternating location procedure from randomly chosen points, or so-called k-means plus procedure, or, for example, probability changing method, or various genetic and other algorithmic frameworks. The evolutionary algorithms are very efficient for these kind of problems, and especially evolutionary algorithms with greedy agglomerative crossover. First, the greedy agglomerative crossover operator was proposed by Alp, Erkut, and Dresner in 2003 for the network Pymerian problem. It uses integer alphabet, and the specific feature of such algorithms, they use no mutation. Then they were adapted for continuous problem. There were several adaptations to make them work faster, to make them work with continuous problem. The ALA procedure was embedded into the greedy agglomerative heuristic procedure. Here we have a scheme of the greedy agglomerative crossover. We have two solutions on the left side and on the right side, two parent solutions. They are represented by the coordinates of the red points, the third points, the centers of the clusters. We merge those solutions, and we have a new infeasible solution with extra number of the centers, extra number of the red points. Then we exclude the centers one by one until we have the desired number of the centers equal to P. Each time we exclude such center which gives after its elimination the best result. And after each elimination, we perform the local search with the Lloyd procedure, with the ALA procedure. This is a known scheme. It is efficient for many problems. It is computationally difficult, but after implementation of such algorithms on the massive parallel systems, we can operate with millions of data points, millions of demand points, and hundreds and thousands of clusters, hundreds and thousands of sort points. But when we move to big problems, these are not real big data problems, but large problems. Nevertheless, the features of the algorithms, they change. And there is always a question for such a scheme. How many centers must we add from the second parent solution to the first solution? The first answer is just one. Then we have an algorithm very close to the J-means algorithm. The second answer is we must merge the whole first parent solution and the whole second parent solution. And there is the third answer. We can add only R extra centers from the second solution to the first solution. And this parameter R, the algorithms are very sensitive to the value of this parameter R. This is the dependence of the results on this parameter for a very popular data set, BIRCH3. It contains 100,000 data points. Here we have 100 of sort points, 100 of centers, and the results are twice different, depending on this parameter R of the greedy agglomerative heuristic procedure. So we have to adjust this parameter. For small problems, this dependence is not so important. We investigated the data sets with different numbers of data points. For example, here we have more than 2 million data vectors, and we try to find 300 of centers, 300 of central points. We investigated both geometrical or geographical problems, problems of facility allocation, and problems of clustering. The popular idea for the evolutionary algorithms is the so-called 1 plus lambda algorithm. This is not a true evolutionary algorithm because the population contains only one solution. So it is very close actually to the local search, but it uses some ideas of the evolutionary algorithms. So first we have a single solution. Then via the mutation, we generate several offspring solutions, namely lambda offspring solutions. Then we select the best of them, and after we work with this new solution, with the best of the offspring. In this algorithm, the mutation rate is this algorithm is very sensitive to the mutation rate. And Dürr and others several years ago proposed the so-called self-configuring 1 plus lambda algorithm. Of course, they proposed such algorithm for usual encoding of the solutions, binary encoding, which is used usually in the genetic algorithms. The idea is very simple. We have only one current solution. We generate lambda of the offspring solutions, but 1/2 of the offspring are generated with the mutation probability equal to 1/2 of the current basic mutation probability. And the second subpopulation of the offspring we produce with the doubled mutation probability. Then if the first subpopulation gives the best result, then we reduce the current mutation probability, and in further iterations we use the new mutation probability. We adapted the same idea for the algorithms with real valued encoding of the solution, and we used so-called crossover-like mutation. What does it mean? First, we have only one current solution. The solution is represented by the coordinates of the central points, x1 to xp on the left side. Then we generate two subpopulations. One half of the population, the first subpopulation, and the second subpopulations are generated first in the same way. We, for each offspring solution, we first generate a new solution. We randomly generate a new solution, for example, S1, S2, S3, and so on. Then we implement the local search ALA algorithm to this solution. So we have the second local minimum. Then for each of the offspring solutions, we implement the greedy agglomerative heuristic procedure. In this procedure, the first solution is our current solution. And the second solution is one of the solutions from the offspring. So we improve all the offspring solutions with the greedy agglomerative heuristic procedure based on the current solution. But in the first offspring subpopulation, we use the reduced value of the parameter R. In the second part, we use the, actually not doubled. Here we have a wrong coefficient in the presentation. We use enlarged value. Here we have true coefficient 1.5. Then, depending on the subpopulation which gives us the best solution among the offspring, we reduce or increase the value of the parameter R. Of course, this parameter is integer, unlike the mutation probability in the initial 1 plus lambda algorithm. In our implementation of such algorithm, we use two kinds of iterations. A simple iteration, which when we actually realize 1 plus 1 evolutionary algorithm. So we have only one offspring solution. And we use so-called iterations with adaptation, or iterations with the adjustment. In the iterations with the adjustment, we generate lambda offspring solutions. We implemented our new algorithm for different data sets up to approximately 2 million data vectors. We used CUDA implementation of our algorithm. We used GPU. Program is written in, of course, C++ with CUDA. And we compared the results with a set of known algorithms. These are our previously developed algorithms, as well as well-known algorithms such as ALA algorithm, of course, very popular J-means in its implementation for the p-median problem proposed by Mladenovich, previously proposed by us algorithms with greedy agglomerative neighborhood. Also various variable neighborhood search algorithms, for each algorithm we made 30 attempts. There are results of the known algorithm, and our new algorithm, it is 1 plus lambda EA with different values of lambda. In several cases, not in all cases, but such algorithms showed the best results. If they show not the best result, then the result is still very close to the best of known algorithms, and the difference is statistically insignificant. Moreover, the new algorithm is faster. So it depends how many time we give to each of the algorithm, but the new algorithm, it shows the best results in a wide range of time limitations. Sometimes it gives not the best result, of course. There is no universal computational tool for this problem. And this is the dynamics of the parameter R during run of the algorithm. Here we use a logarithmic scale for the problem with 300 of thought centers. And we can see that the parameter, it fluctuates in sometimes we have some linear dynamics, sometimes not. Due to these fluctuations, we have better results on various stages of the computation. The best value of the parameter R is different. So we proposed an efficient 1 plus lambda evolutionary algorithm, and our further research, we plan to investigate the same approach to the true genetic algorithms, and also to the k-means algorithms, and to the k-means problem, and to the problem of separating the mixed probability distribution. That's all. Thank you.
Thank you very much for your presentation. Dear colleagues, we have time to ask questions. Evgeny Sobov, please.
Well, as you have said in the beginning, this evolutionary algorithm 1 plus lambda, it's a kind of local search.
No, it's not.
I mean,
it is very close to local search.
I mean that you consequently improve one point using some randomness in different local areas.
Yes, in this sense, it's a kind of improved local search.
I mean that evolutionary, it's a kind of population-based. You need some parallel search of many solutions, but here we have one. So okay, it's a term, just a name.
Yes, this is just a term. We can call this algorithm a VNS algorithm.
Okay.
This is just a question of terminology.
Yes, I see. The question is, if we apply not so advanced parallel algorithm for global optimization, and much simplified version can find good solutions, maybe your problem is not too very hard in a sense of global search.
Okay.
Yeah, I mean, in this case, there exist some special binary search algorithms, random local search algorithms for binary search space. Can we apply one of them instead of evolutionary algorithm?
About the binary search, it was proved by Dresner, Brimberg, and others in 2020, 1 year ago, that the best solution of the discrete problem, discrete p-median problem, is can be very far from the best solution of the continuous problem. That's why the binary encoding is not a good idea for such algorithms. It was proved, and the algorithms with binary encoding, this was our first attempts, but the difference is sometimes very significant. So the better idea is to embed the local search into the iterations of the algorithm and use the algorithms with the real valued encoding. And what about less sophisticated algorithms and more sophisticated algorithms? Here we compared our new algorithm with, for example, swap neighborhood search. We used various swap neighborhoods with various dimension of swap neighborhood, various orders of swap neighborhoods, and choose the best one. Here, the best one is swap one, but we used different ones. And our algorithms give better results. To compare with the true genetic algorithms, it's always a good and very important question. It depends on the time which is given for the algorithm. If we enlarge the time, of course, the true genetic algorithms give better results. If we use shorter time, such algorithms are very good alternative to them.
Okay, thank you.
I have also a question. You say that 1 year ago it was proved that binary decision in binary space and continuous are not close to each other. Such a technical question, it was proved for direct binarization, or for example, gray code has been used.
It was not about binarization. The binarization here, it is commonly used. This problem has two statements. It has integer statement and continuous statement. So this is dual problem, actually. Usually, the researchers use one of two kinds of integer statement of the problem. And for excuse me, for this integer statement, there is no question about the binarization. We have only one choice for each. Binarization by, I mean, direct binarization, I don't think it's a good idea for such a problem.
Yes, that is why I asked it, because it's well known that local optima in binary space and continuous space can be very different, just because neighbor points in binary space can be very far away from each other in continuous space. And one of ways to avoid it was use the gray code. That is why I asked it. Thank you. And the last question, excuse me, for today, saying that your algorithm is faster, did you mean time in seconds or amount of objective function calculation?
Time in seconds. It's very difficult to calculate the times of calculating the objective function. It's because the ALA algorithm, it does not calculate the objective function directly.
At all, yeah.
Yes, and moreover, since we have decreasing solution, first we inflate the solution, then we decrease it. In different iterations, we have different objective function, and the complexity of their calculation is different.
Can be different, yes, of course. That is why I asked. Okay, thank you very much. Okay, maybe somebody else would like to ask a question.
I have a small question, if I may.
Yes.
About applications. I just saw that you use some MOPSI data.
Yes.
Did you have any feedback from the MOPSI project?
No, we used this data only just as a set of points, as geographical data, nothing more.
Mm-hmm. But according to your result, you outperformed some other approaches, or?
Yes, I know we outperformed some approaches. This is our work.
Okay, thank you.
Okay, thank you very much again for presentation and for discussion.